So we're moving on now to the third and final section of the course. And the first lecture in this third section is all about combined loading. And this is where we start taking the individual pieces that you've learned so far and bringing them all together. So thus far, we know that we can get normal stress sigma from an internal normal force, and we calculate that by simply dividing the internal normal force by the cross-sectional area. But we also know that we can have normal stress produced by an internal moment, and we calculate that according to the equation my over I. So we've got two equations for normal stress. And if stress exists at a point within a material due to both an internal normal force and an internal moment, then depending on the orientation of those stresses produced by those individual internal load components, we can sometimes add or subtract them, in other words, combine them together. So that's essentially what we're looking at here. And the same thing's true for shear stress. We have shear stress caused by an internal shear force, and we know that internal shear forces are most often related to moments. And when the shear force is related to moment, then we calculate the value of the internal shear stress at a particular point using the equation VQ over IT. And we can also have shear stresses created by an internal torque. And we calculate those using the equation T rho over J. So in combined loading, we look at when can we combine normal stresses together and when can we combine shear stresses together. Now, we can't combine normal stresses with shear stresses because, remember, those stresses are fundamentally different, where the normal stresses are sort of pulling atoms apart or molecules apart, depending on what type of material you have, or pushing the elements of the material closer together than they want to be, whereas shear stress is that sliding action between the elements of a material. Okay, so the question is, when can we combine? Right, and the same thing for shear stress. Okay, so let's rather than take you through the sort of the theoretical framework here, I think it's easiest to understand this by just starting and looking at a simple two-dimensional example, and then once we're through the 2D example, then we'll look at an example where we have a three-dimensional object. So example. So in this example, we're going to have a beam, and again, this is just a simple example to get the idea across, so we're not going to do anything too complicated here. We're going to put a pin and a roller and a couple of 10 kilonewton loads sitting here, and we'll just make dimensions easy to work with. We'll say that that's 2 meters, and that's 2 meters, and that's 2 meters there. Now, in terms of the cross-section of the beam, we'll just give this beam a rectangular cross-section like this. This will be 100 millimeters, and this will be 300 millimeters. Now, for the problem, in this case, and we haven't seen a lot of beams with this sort of loading scenario yet, but we're also going to add another load. We're going to add a horizontal load here and say that this is 40 kilonewtons. And for the problem statement, what we are going to ask is, what is the total stress at this point here, point A, in the middle of the beam at the top of the cross-section, And what is the stress at this other point, B? So these points are here 3 meters from the end, so right in the center. So the question that we're asking is stress at A and the stress at B. So if we want the stresses at points A and B, we know what we need to do to get the stresses at a particular point. We need to take a section cut through that location and then look at the internal forces. But before we do that, we're going to end up needing support reactions here. So let's put those on. So we'll just change this drawing into a free body diagram here. Now, because the beam is symmetric with respect to the vertical forces left and right, we know that the force over on this pin support reaction in the vertical direction, we'll call that AY, has to be equal to 10 kilonewtons. And we know that BY has to be 10 kilonewtons as well. And you could get those by doing some of the moments about point A and then some of the forces in the Y direction. And some of the forces in the X direction will tell us that support reaction AX here has to be 40 kilonewtons. So now we can go ahead and do a section cut through points A and B to find out what the internal forces are within the beam at that particular location. So let's do that. So drawing what we have there. There we go. So point A is up here, point B is down there. We've got our 40 kilonewton load AX. We've got our 10 kilonewton load AY. We've got another 10 kilonewtons for the externally applied load. And then we know when we section through a bit of material, we can have normal force, shear force, and internal moments. So for our normal force, some of the forces in the X direction tells us that the internal normal force at this location has to be equal to 40. Some of the forces in the Y direction says that the shear force in this situation is actually 0. And then we've got our internal moment here, M, okay, and we usually label that with a subscript, and I'm a fan of doing in some of the moments about the center of the cross section here, where that internal moment's acting. So this is going to be M subscript C, because that's where that internal moment acts about point C. The centroid of the cross section. And if we do a sum of the moments about point C, sum of the moments about point C has to be equal to 0. Take the counterclockwise direction as positive. So you've got MC, and then let's see, plus the contribution from the 10 kilonewton externally applied load. So again, this is 2 meters there, that's 1 meter there. So we've got, this is 10 multiplied by 1 in that same direction. And then the 40 kilonewton load, that passes right through point C when you project it forward, so it doesn't create a moment about that point. And then we've got the 10 kilonewton load from support reaction AY to worry about. Okay, so that's in the opposite direction. So we have minus 10 multiplied by 3 equals 0. So we've got MC is equal to 20 kilonewton meters here. Okay, so let's just flip to a new page here and redraw our section cut with those internal forces on and take a look at them. So let's say something like that, and we've got an internal normal force that's 40 kilonewtons there, and we've got an internal moment, the moment about point C, which is the centroid location or the centroidal axis here, point C. And that value is 20 kilonewton meters. And we've got point A at the top of the cross section and point B at the bottom of the cross section. So what I want to look at is I want to look at what stresses these two internal forces cause over the cross section. So let's consider the internal normal force first. So I'm just going to re-sketch that cross section there like this, and we're just looking at the internal normal force N right now. So we know how to calculate stress due to an internal normal force. It's sigma equals N over A. And all of the points in the cross section will experience the same stress, sigma equals N over A. And because the normal force is compressive, that stress is going to be compressive. So at point A, we've got a normal compressive stress, and at point B, we've got a normal compressive stress. And at every point in between those, we've got a normal compressive stress, sigma equals N over A. And I'm just going to write that as sigma subscript N to denote it as a normal stress caused by the internal normal force N. Okay? So what I've drawn there is the stress profile over the cross section due to the internal normal force N. So now let's look at the stress profile caused by the internal moment MC. Okay, let's just clean that up a tiny bit there. Okay, so we've got our point C right in the center, point A at the top, point B at the bottom, and our moment is acting around in that direction. M subscript C is not 40, it's 20 kilonewton meters. Okay. So we know what's gonna happen in terms of stress due to an internal bending moment that's occurring in that direction. So that moment is going to take point A and push it in to the rest of the material in the beam. So it's going to create a compressive normal stress at point A. At point B, the opposite's going to occur. So it's going to take point B and pull it out from the rest of the material in the cross section, so that's going to be a tensile normal stress. And then in between those, we've got a linear transition moving to no stress at point C, which is the neutral axis of bending for moment MC. So here we've got decreasing compressive stresses moving towards C, and then we've got increasing tensile stresses moving from C outward to B. Okay. So now we can see what the stress profile here, and I'm going to call this stress profile sigma subscript MC for the normal stress caused by internal moment MC. Okay, so we've got the stress profile due to MC. So now what we can do is we can look at our 2 points of interest. So if we were to draw the material at point A, so now at point A, so what I'm going to do here is I'm going to pretend as if we're taking the little square of material that exists at point A and draw it in larger form. Okay, so here's the little square of material at point A. And it's really a cube if we're thinking about this problem having depth into the plane of the screen. But we're just looking at the material here in, well, let's call this the y direction down here and the x direction here. So we're looking at the point of material in the XY plane. So this is referred to as an in-plane element. Now, the side of the plane or the side of the point that's in the section cut here that we've drawn is this side. So that's the side that those internal forces are acting upon, and that's the side that we put the stresses on. So we can see from the internal normal force, we've got an compressive normal stress here, sigma subscript n, and then to keep this in static equilibrium, we need an equal and opposite compressive normal stress on the other side. But also, from the internal moment, we also have a compressive normal stress that's oriented in that same direction. So we have to add that on as well. So this is sigma subscript mc. So you can see now that we've got compressive stresses that both act in the same direction up at point A. So what we can do is we can redraw the element of material at point A, combining those stresses together. So here we've got sigma equals sigma subscript n plus sigma subscript mc. Okay, so this picture down here gives the overall stress state at point A. Okay, so this is the overall stress state at point A. Okay, and now because this normal stress here is occurring in the x direction, as I've just defined down here, then we'd label this as sigma subscript x for the normal stress in the x direction. So we can of course calculate the value of sigma subscript n and sigma subscript nc. So we'd have sigma subscript n is n divided by a, which was 40 kilonewtons. Change that to newtons divided by cross-sectional area, which was 100 millimeters. Was it? Let's go back and check. Yeah, 100 millimeters there and 300 millimeters in height. So let's put that in, 0.3. And what does that give us? That gives us 1.3 megapascals. And then sigma mc is given by my over I, and here internal moment 20 kilonewton meters, 20 times 10 to the 3. Distance y, distance from the axis of bending to the point that we're calculating our stress at. So we're going from that point up to there. That's half the height of the cross section, 150 millimeters. 0.15 divided by I, 1/12 base height, and cube that. Okay, what did that give me? That gave me 13.3 megapascals. Okay, so now with those calculated, we can look at the overall stress at point A again. So at A, we have an overall stress state that looks like this, where we just have a single compressive stress, sigma subscript x, because it's in the x direction, and its magnitude is 1.3 plus 13.3, 14.6 megapascals. Okay. Now let's look at point B here. So let's just clip off this here. Okay. So we have that to look at. Okay, perfect. Let's do a little bit of erasing. There we go. Okay, so if we're doing the same sort of thing and taking a look at the little piece of material that's located at point B here, I can draw a better square than that. There we go. Then we see from the internal normal force, we have a compressive stress. So this is sigma subscript n at point B as well. But then from the internal moment mc at point B, we have a tensile stress. So we've got tensile stress sigma m subscript c. And we know the values for those two things, actually, because if we think about the internal normal force and the stress caused by that, sigma subscript n, it's exactly the same value at A and B, which was 1.3 megapascals. And for sigma mc, the stress caused by internal bending moment mc, the calculation my over I, with this being a rectangular cross-section, distance y is exactly the same to the bottom as it is to the top of the beam, so the value of the tensile stress is the same as the compressive stress, or the maximum tensile stress is the same as the maximum compressive stress. So this is going to be 13.3 megapascals as we calculated before. So we can see that we've got normal stresses, two normal stresses that are acting along the same horizontal axis, which we've defined as the x-axis, and one's tensile and one's compressive. And the value of the tensile stress is quite a bit larger than the value of the compressive stress. So what's going to occur here is that the compressive stress from the internal normal force is going to act to reduce the overall tensile stress that's experienced at this point. So when we look at the overall stress state at point B, so stress state at B, and we look at combining those stresses, instead of one compressive stress, one tensile stress, now we just have one tensile stress, sigma subscript x, and its value is the difference between those two stresses. So we've got 13.3 minus 1.3 equals 12.0 megapascals. Okay, so that's the general idea of combined loading. Now, of course, it's quite a bit easier when you're dealing with two-dimensional problems like this, but it's not so much harder when you're dealing with three-dimensional problems either. Instead of having, let's look first maybe at how many different possibilities of normal stresses and shear stresses we have when we're dealing with a three-dimensional problem, and then we'll talk about the rules for when you can combine normal stresses and when you can combine different shear stresses. Okay, so let's do that. So for 3D problems. Okay. So when we're dealing with 3D problems, let's say now we've got a situation where we've got, something where we've taken a section cut through and we're interested in the stresses, at that particular point. Now, instead of drawing that piece of material as a two-dimensional in-plane element, as we'd call it, we draw this piece of material as a three-dimensional volumetric element. So here we go. So we've got something that looks like this here. Okay, and then we'll show some hidden lines here. There we go. Okay, tidy that up a little bit. All right, so let's talk about the different stresses that can occur in 3 dimensions. And before we do that, we need to define a set of axes for ourselves. So if we take this to be our x-axis and this to be our y-axis there, then using our right-hand rule, this direction here needs to be the z-axis. All right. So first of all, when we draw normal and shear stresses, normal stresses are always acting to extend or compress the material. So the normal stresses are always oriented perpendicular to the surface, or normal to the surface of the sides of a volumetric element. So thinking about the different possible normal stresses that we could have here, we could have a normal stress that acts on the top face of that little cube of material. So that would be, just drawing these in as tensile. This would be labeled sigma subscript y to indicate that it's a stress, a normal stress in the y direction, right? And the naming convention is pretty obvious here. So this is also sigma subscript y in order for the element of material to remain in static equilibrium here. And we could have a normal stress acting on the left-hand face like that, in which case we'd have an equal and opposite normal stress acting on the right-hand face, and that would be sigma subscript x because it's parallel to the x-axis. And then we could have also a normal stress that acts on the front face of the element like this, sigma subscript z. And then again, equal and opposite stress acting on the back face, sigma subscript z. Okay, so those are all the different normal stresses that we can have when we're dealing with a 3-dimensional problem. You can have one normal stress along each of the 3 axes. So 3 possible normal stresses. Okay, we've got sigma subscript x, sigma subscript y, and sigma subscript z. Okay, that's pretty easy. For shear stresses, let's see how many different shear stresses we can have when we're dealing with 3-dimensional problems. So I'm going to draw that volumetric element that I had again. There we go. Like this. And we'll shift it over just a little bit to give us a little bit of space on the page. And then I'm going to make a couple of different copies of it. So let's paste it there again. And let's paste another one over here. Okay. And again, let's set up our axes or our coordinate system. So we're talking about the x-axis, the y-axis, and the z-axis in that direction. So let's think about the different shear stress possibilities that we can have. Now, where normal stresses were always acting perpendicular to the faces of that little element of material, shear stresses are acting parallel to those faces or those surfaces. So we could, for example, have a shear stress that was acting upward on the left-hand side. Okay. Now, if we name this shear stress, instead of shear stresses getting named with one subscript, we actually need to name them with 2 subscripts to define them. So the first subscript tells you which axis the plane that the shear stress is acting on is perpendicular to. So this plane that the shear stress is acting on, so this face of that cube of material, it is perpendicular to the x-axis. So that's our first subscript here, tau subscript x. And then the second subscript tells you the axis that the shear stress is parallel to. So the shear stress is parallel to the y-axis. So that's our second subscript. So we have tau x subscript y. So this is axis that face of tau is perpendicular to, and this is axis that tau is parallel to. Okay, and then we know from our discussion of well, we did this both when we looked at torque or torsion shear stress due to internal torques in non-circular cross sections, as well as in the lecture when we introduced the new equation for transverse shear stress. We talked about the idea of complementary shear stresses and how if we have one shear stress here for static equilibrium, we need to have another shear stress on this side pointing downwards, but now that element still isn't static, so we need to have that complementary pair of shear stresses, one on the top and one on the bottom, pointing in that direction. So those shear stresses all have to be the same as one another, and when you have one of them, then you know you have the three others, so they need to exist in a set of four like that. Now, if you go about naming this other shear stress on the top here, the complementary shear stress, then let's look at this name. So that top plane is perpendicular to the y-axis, and the shear stress is parallel to the x-axis. So you can see that the subscript variables just changed position here. So instead of tau xy, we've got tau yx. Okay, so tau xy and tau yx always have to be equal in magnitude to one another. So that's one possible shear stress that we could have. So instead of a shear stress that acts upwards on that left-hand side, we could have one that acts sort of, pointing forward like this. And in that case, we need to have one on the right-hand side pointing backwards, and then we need to have another two, one like that, and one like that on the back face. And if we think about naming one of these, it doesn't really matter which one we name. How about that one? That is going to be tau. Look at the face that it acts upon. That's the front face. That's perpendicular to the z-axis. So that's tau subscript z. And the next variable, the shear stress is parallel to the x-axis. So it's tau zx. Okay. And then doing that, we automatically know that this is tau xz. Okay, what other possibilities do we have? So instead of having a shear stress that acts to the left on that top face, we could have one that acts forward on that top face like that, in which case we'd have one on the bottom face acting that way, and one on the front face acting up, and one on the back face acting down like that. So if we wanted to name the shear stress on the top face, let's say, this would be tau subscript top face perpendicular to the y-axis. That shear stress is parallel to the z-axis. So we've got tau yz, which would make this one tau zy. Okay. So those are all the combinations of shear stress that can occur in 3 dimensions. So we've got 3 possible shear stresses, right? We can have tau xy, tau xz, or tau yz. Of course, recognizing that tau xy is the same as tau yx, so we won't write those other ones. So there's just 3 shear stresses that are possible. So now the question becomes, so when can we combine different shear stresses, and when can we combine different normal stresses? So if we flip back to our normal stresses here, the rule for normal stresses is that you can combine, and again, this is at a particular point. At a particular point, you can combine different normal stresses as long as they are occurring along the same axis. So let's say at this point in the material, if we had 2 different internal forces that were both producing normal stress along the z-axis, then we could combine those normal stresses along the z-axis. What we can't do is combine a normal stress along the x-axis with a normal stress along the z-axis, or a normal stress along the x-axis with a normal stress along the y-axis. You can only combine normal stresses if they act along the same axis. So we can combine normal stresses that act along the same, let's try that again, the same axis. There we go. Now for shear stresses, the rule about which shear stresses you can combine is as follows. So you can combine shear stresses when the shear stresses act on the same face and they are parallel to one another. Okay. So we can combine shear stresses that act on same face and are parallel to one another. So if those shear stresses that act on the same face are both pointing in the same direction parallel to one another, we add them together, and if they're pointing in opposite directions, they subtract from one another. So pretty simple. So let's do another example, and again we're gonna start off pretty basic here, just to show you how the whole process works when we've got a 3-dimensional object under load, and what we want to do is we call it defining the stress state at a particular point. And defining a stress state means showing a representation of that element of material that exists there with all of the stresses that exist on it appropriately combined. So, example. Okay, so this is going to be a question where we've got a rod here. This, and it's going to be attached to a wall or support here, fixed support on that end. And let's put on some loads here. So we've got a vertical load that's going to be 15 kilonewtons. And what else? We'll just put on a torque at the end. Okay, so this is going to be a torque of 3 kilonewton meters there. And let's say that this rod has a diameter of 100 millimeters. And for some reason, what we are interested in is the stress at point A here, which is on the outside of the rod at a distance of 2 meters from the end of the rod. Okay, so the question that we want to answer is this, or the statement. We want to define stress state at point A. Okay, so we want to define the stress state at point A. Okay, so the system, or the steps that we want to go through this. So I'm going to sort of teach you how to do this by laying out some steps here. So the basic procedure is the following. So we find out what the internal forces are in the plane of our point of interest. So that's in the section plane of point A. And then we go through those internal forces one by one, figuring out whether they cause stress at A, and if so, what stress they cause and what the magnitude is. And then we look at all of those resulting stresses and figure out which ones can be combined, which ones can't be combined, and then appropriately combine them and draw an overall picture of the element of material at point A with the combined stresses showing. Okay, so the first step is find the internal forces at the location of A. So find our internal forces. Okay, so to do this, we're going to take a section cut through point A, and we'll put on our internal forces there. So I'm going to draw this again. Here we go. So we're taking it up like this, and then we've got our section cut that we've done. Now that's going to be like this. Right, there's our cut edge. Perfect. Okay, that looks better. So now we've got 15 kilonewtons there. We've got 3 kilonewton meters there. Okay, and then we want to put on, so here's our point A over here, and then we want to put on our internal forces. So the easiest way that I personally find to do this is, first of all, take your coordinate system, and we don't have one laid out yet, so we want an overall coordinate system for our object here. But I'm going to take that coordinate system and I'm going to position it right on the centroid, with its origin on the centroid of the section cut that we've made here. So I want to set up my axes like this, where I'm going to call this axis here my x-axis. I'm going to call this my y-axis going up here, and then this is going to be my z-axis going out that way. So now what we need to do, now that we're dealing with 3 dimensions and we want to find the internal forces, is we've got 6 equations of statics to deal with. So just like to write them, what they all are, down, and then go through them one by one and figure them out. So we need to do the sum of the forces in the x direction equals 0, sum of the forces in the y direction equals 0, sum of the forces in the z direction equals 0, sum of the moments about x equals 0, sum of the moments about y equals 0, sum of the moments about z equals 0. Now, after you write those all down, now you look at those 6 equations there and figure out which one you've made the mistake on, because one of those sum of the moments equations is actually a sum of the torques. And figuring that out is important, again, because you know that an internal moment causes normal stress and an internal torque causes shear stress. And if you go about doing a sum of the moments equation and calling an internal torque a moment, then you're going to end up calculating normal stress instead of shear stress. And that's going to throw everything off entirely. So the z-axis is the longitudinal axis of this object, so we shouldn't be doing some of the moments about z. We should be doing some of the torques about the z-axis. Has to be equal to 0. Okay, so let's start with x. No applied forces in the x direction, so there's not going to be any internal forces in the x direction. So we've got 0 equals 0 already, so we don't need to worry about anything there. Some of the forces in the y direction. We've got 15 kilonewtons down, so we need to have 15 kilonewtons upward. Now that force that I've just drawn is an internal force. It's parallel to the cut section that we've made, or the section plane that we've made. So it's a shear force. And because it's an internal shear force and it's in the y direction, I'm going to label it V subscript y for the internal shear force along the y-axis. Okay, so we've done that one. In the z direction, we don't have any applied loads, so there's not going to be any internal force. If we did have an internal force in the z direction, that would be an internal normal force, but we don't have one. Now, some of the moments about the x-axis here. So what is helpful, I think, to do is consider holding the x-axis in your hand and thinking about which of the applied loads would cause that axis to rotate around in your hand. So in either one of these directions there. And we can see that the 15 kilonewton load would cause the object to rotate around underneath the x-axis, or in the counterclockwise direction looking down the x-axis. So we need an internal moment about the x-axis in the other direction. So there we go. That's our internal moment about the x-axis. So the value here of m subscript x is equal to 15 kilonewtons multiplied by the distance, which is 2. So we've got 30 kilonewton meters here. All right, and you should be pretty good at this from your statics course that you've taken. All right, moving on to the y-axis, we don't have any applied forces, external forces that are going to cause a moment about the y-axis. Remember, to cause a moment about an axis, you need to have a component of the force that is perpendicular to that axis and separated from it by some distance in space so that the projection of the force and the axis don't cross one another. The 15 kilonewton load is parallel to the y-axis, so that's not going to create a moment. So no applied or no moments about the y-axis from the applied loads, so no internal moment about the y-axis. The moments about the y-axis are already balanced equal to 0. So we don't have to worry about that. Torques about the z-axis, this one's easy, right? We've got 3 kilonewton meters that way, so we need an internal torque here that is, actually that might be confusing if I put it on there, so let's project this back out that way and put it on at the end. So we need one that's going that way. So let's just move our label for mx down here, and then this is T subscript Z, our internal torque about the z-axis in the opposite direction as the 3 kilonewton meter applied torque. Okay, so we've done this one too. So now we've got our internal forces taken care of. Okay, now I'm just going to grab this and take this with us to the next page. And actually, the only part that I really need to take is this part there. But it would be helpful to first put in what the values are. So we want this to be 3 kilonewton meters, and this to be 30 kilonewton meters. Okay, so now we're ready to do our copy paste. Okay, so step 2. So after you've done the internal forces, step 2 is to draw the volumetric element at your location of interest and indicate the face that's in the section plane. So draw volumetric element at location, or this should be at point of interest, really. Point of interest. Okay, so if we draw the material at point A in the same sort of perspective as our overall drawing here, our coordinate system, then we've got a little piece of material that looks like that. Okay, there we go. So that's supposed to be a perfect cube. So this is, right, this is that little bit of material at point A blown up into a larger size, right? Let's try and make that side a little bit better. There we go. Okay, so that's actually a little bit of material that exists at point A. Okay, there we go. Now let's put on our axes, or our coordinate system over here, so we remember which directions are which. So we've got X, Y, and Z here. Okay, now the next important thing to do is identify which face of this element is in the section plane that we've cut. So it's that back face there that is in the section plane that we've taken, right? And the rest of that element projecting forward along the z-axis projects into the body of that rod. So the back face of that element is in the same face as the cut face of our object here. And that's important because those internal forces that we've identified, Vy, Mx, Tz, those all act on that cut section. So the stresses that they create are acting on that red face, the back face of that cube that we've outlined. So as we figure out what stresses are created by those internal forces, we're going to place them on that back face of the element. Okay, so now what we do is we go through the internal forces one by one, figuring out how they create stress at point A. Okay, so this here, this is point A, right? That whole cube of material is point A. So 3, go through internal forces one by one, determining create stress at point of interest. Okay, so let's go ahead and do that, and we'll keep flipping through back between the page that we're on and our pages that we've left here. Actually, you know what's a better idea? A better idea is just to take this and do a little moving around again, so we retain this at the top of the page. That would be better. Okay, so let's put that like that, and we'll take this and we'll just move it up there. Right. Just get rid of this here. Okay. So this is point A down there. And again, let's just put our axes on so we don't get this mixed up. X, Y, and Z. Okay. So let's go through our internal forces one by one. So let's start with our shear force Vy. Okay, so if you're thinking about, when you're thinking about each of these internal forces in turn, I think it's helpful to just draw a two-dimensional sketch looking at how the internal force is related to point A and the stress distribution that's caused by that internal force. So if we take a look at our cut section here, just in a two-dimensional view, looking at the object in the y-x plane. So we're looking down the z-axis, and if we look at it like that, point A is over there on the right, and the orientation of Vy is acting upwards like this. Okay, so we know what the stress distribution is going to be like from a vertically oriented shear force like that, right? We know that we're going to have 0 shear stress at the top and the bottom of the section, and shear stress is going to follow a parabolic profile reaching a maximum at the location of the centroid, which is at point A. So at point A, we're going to have a shear stress, right, tau caused by Vy, tau subscript Vy, that is in the direction of the internal shear force Vy. So in order to place that stress on our volumetric element at point A, the only thing that we have to do now is we have to go to the face of the element that's in the section plane, which is the red outlined one, and place a shear stress, right? That's going to be a vector that is parallel to that face, and it needs to point in the positive y direction. So we just go to that back face here and put a stress like this, and this is tau subscript Vy. And now we can figure out what the value of that stress is. So we've got tau Vy is going to be given by Vq over IT is 15 kilonewtons, so 15 times 10 to the 3. Q A prime y bar prime, if we're calculating our shear stress at point A, then what we're really doing is calculating a shear stress at any point along that line, which means that our area A prime is that area right there, either that one or the area below. So we've got for our area A prime, pi over 4d squared divided by 2, so that's pi over 8d squared. And what did we say? This was 100 millimeters in diameter? Yeah, 100 millimeters in diameter. So 0.1 to the 4, so that's that semicircular area. And then the centroid location, so we want the centroid of A prime, which is there, relative to the overall centroidal axis for the entire cross section. So this distance here is y bar prime, and that is simply the centroid location of a semicircle relative to its base, which is 4r over 3 pi. So 4r over 3 pi, or 4d over 6 pi. So 4d over 6 pi there. And then we divide it all by I, pi over 64 d to the 4th power. And now I'm realizing that we've got a mistake here. This should be squared up here because that's area, pi over 4d squared divided by 2. Okay, so on the bottom here, we've got I now, and then we've got T. T is the length of the line that you're calculating shear stress along. So that is diameter again. So we've got another 0.1 down there. So doing that calculation gives me 2.5 megapascals. Okay, so this guy here is 2.5 MPa. Okay, so now let's look at our next one. So I'm just going to take everything that we had up here and copy this to the next page. So we've got it all with us. Copy. Okay. Paste. Okay, great. So we've got Vy taken care of now. So now let's do our moment mx. So again, a little two-dimensional drawing I think is helpful. So in this case, what you'd want to look at is, and your 2D drawing, you just choose to do a drawing where you've got the best view of the stress that's being created by the particular internal force that you're dealing with. So here, what I'm doing is I'm drawing our section so that our y-axis is pointing up like this and our z-axis is pointing back like that. So I'm looking down the x-axis, and if I do that, our internal moment mx is acting about the cross section in that direction. And point A is located right here on the x-axis. So we know what a moment is going to do in that orientation. So it's going to take the bottom of the cross section, jam it in, take the top of the cross section, pull it out. Nice linear transition between those. At point A, there is no stress caused by the internal moment mx. Why? Because point A is on the neutral axis of bending for mx. So no stress at A due to mx. And that's because A is on the neutral axis of bending for m subscript x. Okay, so let's flip our page then and repaste what we were using to look at this. There we go. So now the only stress that we have left to do is the stress caused by the internal torque T subscript Z. So we're going to do a sketch for this where we again look at our cut cross section just in a two-dimensional view like this, where we have the z-axis just appearing as a point. So we're looking down the z-axis, and appearing upwards is the y-axis, and appearing off to the right is the x-axis, and point A is located there, and TZ is oriented in this direction. Okay, so the shear stress caused by an internal torque is easy. We know that at any point that we want, let's say point A in this case, right? We know that the shear stress is oriented tangent to the circumference, or tangent to a radial line connecting your point to the center, and oriented in the direction of the torque. So we've got a shear stress, tau, Tz, right? A shear stress, tau, caused by Tz, tau subscript Tz, oriented in that direction. We know that if we were to look at other points along this line, they'd have shear stresses like that. So shear stress going from a maximum value at point A down to a value of 0 at the center of the cross section. Okay, so again, easy to place the shear stress on our object. What we want to do is we want to place a shear stress on the face of our element at point A that's in the section plane. So that's the red outline face, and that shear stress needs to be oriented in the negative y direction. So just go over here and create a shear stress that's acting downwards like this, and this is tau and then T subscript Z. And again, we can calculate the value of this. We know that tau, that's supposed to be a tau, not a t. Tau Tz is going to be given by the equation T rho over J. And what do we have there? We've got our torque is 3,000, 3 kilonewton meters, multiplied by rho. That's the distance that our point is radially from the center, or the centroid of the cross section. So that's going to be the radius in this case. So we've got 0.05, 50 millimeters, and J, pi over 2 radius to the 4th power. And that is giving us 15.3 MPa. Okay, so this is 15.3 MPa. Okay, so now let's just take this portion with us here. So copy that. Okay. So now we can see that we've considered all of our internal forces now. So these are the stresses that we're left with, and we can see that we've got 2 shear stresses. They act on the same face, and they're parallel to one another. They're in opposite directions, so we can subtract those from one another. So what we can do now is draw a picture that represents the stress state at point A. So stress state at A. Okay, so we'll just draw our cube of material at point A again, like this. Okay, let's move this up a tiny bit. Well, let's put our axes in. So we've got X, Y, Z. And what we're going to do is we're going to take those 2 stresses and combine them, and we can see that the overall direction of the combined stresses is going to be in the orientation of tau Tz, so downward, right? So there we go. Now we can label this stress properly. Now, so we've got tau, and that face that it's acting upon, the back face, is perpendicular to the z-axis, and the stress is parallel to the y-axis, so this is tau zy, and its magnitude is going to be 15.3 minus 2.5, 12.7 MPa, 12.7 megapascals, if you keep all the decimal places from those previous calculations. And then we're not done yet, because we show the complementary shear stresses here. So we've got 1 shear stress on that face that acts upwards, and a shear stress on the top that acts like that, and 1 on the bottom face that acts like that. So there's the answer to our question now. So we've got that picture with that one stress that's labeled with the magnitude correct direction. So now we've defined the stress state at point A. Okay, so I hope that gives you a good idea of what combined loading is all about now. In the next lecture, we're gonna look at how the idea of stresses that exist at a point is influenced by the orientation in which you analyze a problem. Okay, so I'll see you then for lecture 14.